I was to draw a sketch of y equals x and y equals root x. Just going to look at the positive quadrant because it's talking about x being greater than or equal to 0. So y equals x will look a little bit like this. Okay, I haven't put the scale on, but it's going to be a straight line, and it is where the y and x have the same value. Then y equals root x looks a bit like that. Just need to find out where they intersect. So that would be here. And actually, sorry, let me just say that y equals root x, try and think of it like it's a parabola, but it's going up the x-axis rather than the y-axis. That is precisely what it is, because if we were to square it, we have y squared equals x. So x equals y squared. So it's going to be, there's just going to be a very strong similarity between y equals x squared. We don't include the negative value because by definition, we're taking the positive square root here. So that's one way to remember the root of x. If we want to find the coordinates where they're equal, well, you might already know it's actually going to be 0, 0 and 1, 1. If you didn't see that, then what you can do is actually we'll get it all on one side. So root x minus x equals 0. And actually factorize out root x. 1 minus root x, because root x times root x is x, equals 0. So either root x is 0 or root x is 1, from which scenarios we get 0, 0 and 1, 1. We're then asked to look at our sketch, reuse it, and explain why there exists a value of x, a, where a is greater than 1, such that the integral from 0 to a of y equals x, so the area underneath this straight line, is equal to the integral of root x between 0 and a. Now, let's just have a look. What if we use 1 as our starting point? Well, we can see that the root x will have a larger area. So this bit would sort of, this one would be greater. The right-hand one will be greater because we get this extra purple region. I'm going to call this region R1. If we were to increase a, however, this value of x, then when we go above, suddenly y equals x has a greater area in this region here. And you can see at some point it's going to sort of cancel out. You're going to get large enough because this, I haven't shown it on the sketch, but this will carry on and this will carry on. So actually at some point, maybe here, that's when we're going to get the two equaling each other. So I'm going to call this one R2. And then we just really need to explain this. So I'm going to write y equals root x is greater than y equals x between x equals 0 and 1 by R1. So the area underneath will be larger. Also, the integral will be larger. However, after x equals 1, y equals x is larger. At some point, x equals a, the region R2 will equal R1. And at this point, the integrals will be equal. I feel like that's enough justification, some words to that effect. I hope I've convinced you. You can see that, this is the extra bit you get up to zero to between 0 and 1, but then from 1 to A, I label this A, we get an extra amount for y equals x, and so at some point they'll balance out, and that means that the integrals will be the same. We're asked to find the exact value of A. So here's our integral. This is part C, by the way. I didn't, did I? That was part B, and this was part A. So we can just integrate. We're going to get a half x squared by increasing the power by 1 and dividing by the new power, evaluated between 0 and A. Remember, root x is actually x to the half. So increase the power by 1, divide by 3/2, which is the same as times in by 2/3. That's our starting point. Now substitute in the limits. Half a squared, we're not going to get any effect from the 0, will equal 2/3 a to the 3/2. I can divide through by a to the 3/2 and multiply through by 2. So I'll get a to the half is equal to 4/3. Now that's the square root of a, remember, square root of a is 4/3. So a will square each of these will be 16/9. That is the value of a where the two integrals are equal. In part D, we're asked, hence or otherwise, find a non-constant function f of x and a constant b, but b is not equal to 0, such that this is true. Or a natural inclination is to try and use the same function that we already have information on, or that is nearly the same function, because um, we can't do the integral of root x between it. But what about if we let f of x equal the modulus of x? So now we're going to get this going on, and the modulus of x, if x is positive, remains the same. So we've got this sort of thing, the same as before. And remember, we know that there's this value here, 16/9, where these two are the same. Now, if we look at the minus when x is less than 0, f of x will equal it will equal minus x. I'm not going to get into lots of details on the modulus, but basically that will get a double negative, because when you find the modulus of -2, it becomes minus -2. And so we'll get a graph that looks like this. And the square root of f of x will equal the square root of minus x, but this will be greater than 0 now. This will exist. it would actually just look like this. It would be a reflection. And therefore, due to symmetry, we'll get this area here and this area here at minus 16 over 9. And that's it really. So what did the question say? Find a non-constant function and a constant b. Oh, so we're done. F of x is the modulus of x, and b is 16 over 9. This is, I feel like, the most natural way of doing this question, using what we have from before. Just for info, another way of doing this question would be to take the function that we have, and we know that it's between 0 and 16 over 9, it's the same. So if we translate in the negative x direction by half of that, that is 8 over 9, we're going to get something that looks a little bit like this. So that would be minus 8 over 9. So it's not perfectly to scale, but hopefully you can see what I'm getting at. So this would nicely give us our minus b and b. And to translate by 8 over 9 in the negative x direction, it's going to be x plus 8 over 9. And that would work, when you take the square root of that, you would get this green curve, and then b would be 8 over 9. So that's another option.